Welcome to this deep dive into the heart of data science and machine learning. Today, we address a fundamental question. How do we know if our models actually work? Imagine a student who memorizes every answer to a specific practice exam. When they take that exact same exam, they score a perfect 100%. But when faced with a real-world problem they haven't seen before, they fail miserably. This is the in-sample trap, and it's the most common mistake in predictive modeling. In classical statistics, we often fall in love with R-squared, the coefficient of determination. It tells us how much of the variance in our data is explained by our model. However, R-squared is inherently optimistic. It measures how well we fit the past, not how well we predict the future. In the world of econometrics, as described by Gujarati, a high R-squared can often be a fool's gold if the model is overfitted to noise rather than signal. Let's visualize the danger. Imagine data points scattered on a plane. A simple linear regression tries to find a trend, but a complex high-degree polynomial can wiggle through every single point. This complex model has a perfect R-squared of 1.0, but it's capturing random noise. This is overfitting. In machine learning, we say the model has memorized the data instead of learning the underlying patterns. To solve this, we introduce the train-test split. We divide our data into two distinct sets. The training set is the textbook, the data the model uses to learn parameters. The testing set is the final exam, unseen data used to evaluate performance. If a model performs great on the training set but poorly on the testing set, we know it has failed to generalize. This brings us to the fundamental bias-variance tradeoff. High bias happens when a model is too simple, underfitting. High variance happens when a model is too sensitive to small fluctuations, overfitting. Our goal is to find the sweet spot, where the total error, the sum of bias squared, variance, and irreducible noise, is at its minimum. Why is R-squared dangerous? Because in-sample metrics can be artificially inflated by adding more variables, even if they are irrelevant. This is why we use adjusted R-squared in statistics, and more importantly, out-of-sample metrics like mean squared error or mean absolute error on the test set in machine learning. Beyond a simple split, we have K-fold cross-validation. Instead of one split, we divide the data into K groups. We train on K-1 groups and test on the remaining one, repeating this process K times. This ensures that every data point gets a chance to be in the exam, providing a much more robust estimate of how the model will perform in the wild. Finally, we must guard against data leakage. This happens when information from the test set leaks into the training process, for example, calculating the global average of a variable before splitting. It's like a student accidentally seeing the answer key before the test. To build reliable AI, we must maintain a strict Chinese wall between our training and testing environments. In conclusion, never trust a model that hasn't been tested on data it hasn't seen. Whether you are using traditional regression or advanced neural networks, generalization is the only metric that truly matters. References: Basic Econometrics by Damodar Gujarati and Introduction to Statistical Learning by James, Witten, Hasty, and Tibishari.